So one of the things in wireless is that you cannot do collision detection. And the reason you cannot do collision detection is because of the hidden node problem. So here is the situation. B can hear A and B can hear C, right? But A cannot hear C. So when both of them talk to B, they will collide but not know that they collided. Alright? So A can hear only people who are in this red circle, C can hear only people who are in the blue circle, and B can hear people in this black circle. So B can hear both A and C. Actually, I could probably make the circle bigger and then collide, but they will not know each other that they collided. I mean, actually, they are colliding anyway because B can hear both of them at the same time and they will collide. So we cannot do CS-MACD. So we'll have to fix that one with something else. We cannot do collision detection. But the book goes ahead and tells about the whole range of standards. So it's basically pointing out the names, not really much more than that. Is that there are many wireless standards depending upon the speed you want to go to and the distance you want to go to. Generally, the speed goes up as you go shorter distance and goes down as you go longer distance. So if you want to go very short distance, you can go very high speed. If you want to go miles apart, then you go lower speed. So here are the standards up to this point. These are cellular standards. Most of these are cellular standards like UMTS, WCDMA, HSDPA, CDMA, EVDO, and so on and so forth. So these are all cellular standards, and unfortunately in this class, all we're going to do is just throw all these acronyms at you and tell you that these are cellular standards. There's a whole class on wireless networks where we go each of these standards, each word, IS-95, CDMA, GSM, in a class, something like that, right? Unfortunately, we cannot do that here. But so the idea is that you just need to know a few numbers. Here, 11, you already know 802.11. That has A, B, G, N. And 16 is WiMAX, and 15 is basically there. Now the thing is, and then these are all cellular. Cellular go a long distance, but the speed is very low, less than 4 or 5 megabits. WiMAX goes long distance, but the speed is higher. And then AGN, they don't really go too much distance, but then the thing is, with certain techniques, you can make them longer distance. They are designed for shorter distance, mostly indoor. So this is basically giving you some names here, and that's really not very good, but that's all we can do in this particular level of the class. So there are many things that affect the range. It's just not only the frequency of the protocol, but it also depends upon how thick are the walls, whether there is a mirror in the room. Just like light, how much light gets into the room depends upon how thick is the glass, and how much reflection there is and all that. So similarly, wireless is very variable. You could put the same router and the vendor is saying that this goes to 400 meters and in your home it goes to 4 meters. Well, you have two thick walls. Or they go straight cut. I mean, in my home, it's not a very big home, a small home, but Wi-Fi doesn't go through all part of the home. And so you just have to find the right place in your home to put it so that you can get maximum coverage. There are so many variables. Okay, everything can offset the signal. And if nothing else, it also depends upon what other devices you have, and everything uses the same frequency. So 2.4 gigahertz is used by microwaves, that's why it is called microwave frequency. It is used by your cordless phone, it is used by Wi-Fi, and anything else that you have got wireless in your home is using probably 2.4 gigahertz. So when they go on, your devices cannot really operate. Alright, so let's see. I kind of feel bad about just throwing these symbols at you, but CDMA you know already. CDMA is code division multiple access, and it has 3 versions: CDMA 1, CDMA 2000, and then CDMA with EVDO. Yeah. So in 2G, it's only voice. Okay, 3G adds data. All right. Even though 2G is designed for voice, you can get data at very low speed. Like in GSM, if you use GSM like in Europe or other countries, even in USA, you get very low speed data. But if you want really high speed data, then you go to 3G. So 1G is analog, 2G is digital but voice only, 3G is voice plus data. 4G is very high speed data. Now 4G was supposed to come at 1 gigabit. However, several things have come in between, like WiMAX and other things, which are really 3G, and they are being marketed like 4G right now. They are not 4G, but they are marketing so heavily that ITU may decide to call 4G 5G. Because 4G is already here, and people will be confused. So they may change it. But just 2 years ago, when we were designing 4G, 4G was not here. But now in the last 2 years, everybody is selling 4G, Verizon to Sprint, everybody else. But this is not 4G, this is what we would call 3.5G. Similarly, there is a 2.5G which was being sold as 3G by AT&T. So what do? I mean, this is all marketing thing, okay? All right, now, what is LTE? All right, so what is happening is, basically, let me continue along this line, is that we had 2G and 3G, and there were lots of things in between, like 2.5G. And this speed keeps going up. Then WiMAX came along. WiMAX, people said, why don't we take the best of Wi-Fi and give it to the long distance best of cellular and combine it together? So that was WiMAX. So WiMAX allows you to light up a whole city with one tower on the top of the mountain. Again, Subo, and you, yeah, please close the computer. And so, top of the mountain, and then you can light up the whole city, just like a cellular. Okay, but it will do it at 20, 30, 40 megabits per second, up to 50 megabits per second. Okay, and obviously everything depends upon the distance. If you are for 50 miles away, you might get 1 or 2 megabits, something like that. Okay, so that was called WiMAX. WiMAX came around. The main problem with WiMAX was that it was designed by the computer people, Intel, HP, Cisco. All right. And not by the telephony people like Qualcomm, Ericsson, and they felt that they're losing the whole market. Qualcomm in particular, which had the complete control over 3G, CDMA, with all their patents. So then they invented LTE. LTE took everything that was WiMAX, because WiMAX is an open technology, and so anybody can make it, and so on and so forth. They made minor changes and said this is what the telephone company needs. And so LTE is basically same thing. You have one tower which gives you high speed over long distances. And there are other standards which have happened like that same way. So now LTE is the one that everybody is doing. WiMAX is gone. And the book talks about WiMAX, but basically WiMAX is computer people invention. And so we have two kinds of heads. You have heard of bell head. So there are two people, the bell head and the net heads. Most of you in this room are net heads because you are really computer people. The bell heads work for the phone company. Right? Right, Bell Labs. And they think differently, and so ATM was a Bell head technology, and IT people didn't accept it. So there is always this kind of tussle going on between the two industries. Wi-Fi is personal. WiMAX is a company. I mean, like WiMAX can be offered only by a company. I mean, nobody wants to light up the whole city for themselves, right? So this is a metropolitan wireless technology, and it is to be offered by a company, generally using a spectrum that they have bought so that nobody else can put the same service in the same city. Like if we all use 2.4 and 5 people start offering, then nobody will succeed. Actually 5 is okay, maybe 7. So some number of people will collide too much, right? So WiMAX is designed for that kind of thing. All right. So we are getting there, right? So basically LTE is being offered by everybody now. LTE is offered by AT&T. LTE is offered by Verizon. And last but not the least, last week or this month is Sprint. Sprint was the one who was given $1 billion by Intel to start WiMAX, and they gladly accepted the money. And they started working on WiMAX, and they were the leader. But as soon as they said we are working on WiMAX, their stock went down because they said you are working on a new technology, losing money and all that. So they immediately had to branch off that part of the people and call them Clearwire. So they gave the technology to Clearwire, and they were still going to use WiMAX because Clearwire was owned by Google, Sprint, Intel, and whatnot. But now the situation is different. Sprint is going to do. Last month, Sprint announced that they were going to use LTE. All right, with so much introduction to all these different, let's go on to the 11. 11 is originally when invented was 2.1 to 2 megabits. So in 1990s, first when the 11 was invented, it was 1 or 2 megabits. Pretty soon people found out that nobody likes it. 2 megabits, who cares? So they had to change it to 11B, and that gave you only 11 megabits instead of 1 or 2. It gave you 11, close to 10 megabit Ethernet at that time. And it uses the same coding CDMA. Actually, DSS is another name for CDMA, direct sequence spread spectrum. So remember I told you that it's called spread spectrum. So that one is what is used in the physical layer. And all hosts use the same chipping code. So everybody uses the same code so that everybody can hear it, everybody else. So unlike the other where everybody uses different codes and uses and shares it, here it was used more basically so that many networks can share it. So one network, second network, third network. And then people felt that was not fast enough, so then they designed two technologies for 54 megabits. One was called A, one was called G. A required a new spectrum, 5.8 gigahertz, and nobody wanted to go to 5.8. So they invented G, which will work in 2.4, and that way, you could have the same logic wireless technology, which can use both B and G. With A, you need some new hardware. Then they invented N. N runs at 200 megabits, up to 200 megabits, uses multiple antennas. If you see 2 or 3 antennas coming out, 2 antennas is standard, but if you see 3 antennas coming out, then you know it is N. And it can run either spectrum and gives you 200 megabits. And there are many different file layers, but all of them have the same MAC layer. Now by file layer I mean, coding, CDMA, things like that. There are many different ones, and we are not going to go through those here. But they all have the same MAC layer. And media access control, we are going to talk about that a little bit. All of them use CSMACA, collision sense multiple access collision, carrier sense multiple access collision avoidance. So carrier sense, before you speak, you listen, right? But you cannot do collision detection, so what you do is you do collision avoidance, and the way you do that is in the next slide. And all have base station and ad hoc network scenarios. All support multiple priorities and time critical and data traffic and power management. And biggest thing is that most of the wireless devices, including your cell phone, your wireless, they allow you to go to sleep. And most of the cell phones are always sleeping, even though they look like power on, but this phone is off. Okay? This phone is off. It's actually on, by the way. If I press the button, it will come on, right? But what it is it's sleeping. Only every few milliseconds it wakes up and checks with the base, is there anything for me? If there is, nothing, it goes back to sleep. And that's how the battery life has gone up. Not because the batteries have become better, because the users have become better. Yeah, so basically what happens is, and that's again an advanced level question in the sense that they answer this in the wireless class, but I will try my best here, is that if you have the same access method, if you have one G method, then you start using that CDMA or whatever version of the coding you're using, and then everybody has to use that method, and that's why you come down to the common denominator, right? And so really you can't get the advantage of N unless you have everything N, and you can't ensure that the guest will have N. It might have N, But when the guest will come, sir, you cannot use my Wi-Fi because it is all N. So you really need ABGN. So everything actually nowadays is ABGN, but then the question is everybody N or not? So we finished that, and I just wanted to make sure about the power management. Alright, so we've done that. Now the question is, how do you find somebody? How do you find the base station? There are two methods. One is you ask, second thing you listen. So every base station is announcing periodically every second or 2 seconds saying that I am here and my name is Bufi, Bufi. I am here, my name is Bufi S, my name is guest, whatever. So all of these base stations are announcing their SSID, their IDs, right? And you are listening. So your computer is listening, and then it goes through that, and it has a list of what it is supposed to connect to, and it selects the best and connects it automatically. Right? You saw my list somewhere I was connecting. Anyway, so that is one way. Second thing is, if you come to a room, you can say, you know, who is here, and you can ask. So either way, either by scanning. Passive scanning means just listening. Active scanning means, you know, just basically asking. All right. Third thing you could say is that, is there Bufi S here? You could send a very specific message, and then if there is Bufi S, it will say yes, I am here. And so that is a common thing, is that you don't announce your SSID. You can program your router or you program your base station so that it doesn't announce, but anybody who knows the name can basically will ask for it. This is more secure than broadcast. So if suppose it was saying Bufi S is here, then the person doesn't even have to ask for it, and it knows Bufi S is here. But the thing is, at least you have to guess the name. You have to guess the name that Bufi S could be here. And the way you do that, the Bufi S could be here, is in your computer you program that my preferred network is Bufi S. If you don't find it, then only go to this second one. In fact, every computer, every laptop has a list of these SSIDs in order list. It tries to go to the top one first. And you should keep that list in order, because basically what it does is it keeps the last one used first and keeps changing the list, so you have to just, put the top one first, Right? Okay. So you can send a probe request, or you can listen to the broadcast, but it doesn't simply mean that if you can hear to them, you can connect to them, because there are other security things that you have to do. You have to do authentication. So how do you divide collision detection? Basically, before you send, you have to do a 4-way handshake for every packet. Okay? Not like a TCP connection where you do the handshake only for connection. But here, every time you send a packet, you say, I am ready to send, and I want to send a message which is 1500 bytes long, please. Then the access point will say, clear to send. Yes, go ahead and send a 1500 byte message. Then you send a 1500 byte message, and then we'll say, I got it. 4 messages just to send that one 1500 byte message. Why? Because if somebody else wants to send a 1500 byte message at the same time, with this method, less time will be lost. Both of you will say we are ready to send, and none of you will get clear to send. Yeah, what we are doing is you just listen that nobody in my neighborhood is speaking, and hopefully it will reach the base station. And if the base station doesn't listen to anybody else, the base station can detect collision. Right? Base station can see I am hearing 2 people at the same time. If the base station hears one clearly, then it can say to that person, okay, clear to send. And these are very short messages. These are very short messages. So very small time will be lost if you collide or not collide, right? Once you have been cleared to send, base station is broadcasting, so everybody can hear base station. If they are connected to base station can hear everybody, and everybody can hear base station. Right? So everybody will hear this clear to send. Once you hear clear to send, then you are not supposed to try other than your own. So everybody will not transmit them for 1500 byte time. Once you get clear to send, nobody will send anything. Everybody has to listen to clear to send, and clear to send has a time in it. It says you are allowed to send 1500 bytes. For that time, you are supposed to be quiet. No ready to send during that time. In fact, no ready to send for the rest of those. In fact, now here again, I'm just trying to simplify these things here, because here all it is saying is that everybody hears this, and it tells everybody that please stay off the network for that much time until you hear the act, and after the act you do whatever you want to do. So anyway, so this will send the data, and this will be always good. You don't lose 1500 byte simply because you got collided in the last byte. Right? These are very short messages. So you do 4 messages for each message. And this is what we call CSMA-CA. Collision sense, carrier sense, multiple access with collision avoidance. Alright, CSMA-CA. Listen before you talk. If the medium is busy, the transmitter backs off for a random period. Avoids collision by sending a short message, RTS, and tells everyone to back off for the duration. The destination sends clear to send. You cannot detect the collision, so therefore every packet is ACKed, and the MAC level retransmission if not ACKed. So that's the new thing which I didn't talk about so far, is that if you do not get this last ACK, then you retransmit the packet. On Ethernet we don't do that. On Ethernet there is no ACK in the first place, right? And there is no retransmission. But in Wi-Fi it is retransmitted. Alright? Okay, so let's move on to the next one. Ad hoc. You can just put it here. Ad hoc. So basically what happens is each access point has a set of stations that it is connected to, and this is called basic service set. BSS. I'm coming to that. Let me finish this slide. And then, so there might be many access points and many BSSs, and they're all connected by wire in the background. This is called the distribution system, right? And then there are some stations which are not connected to the access point, they are talking computer to computer. This is called the ad hoc network. If somebody says public Wi-Fi but is a computer, you don't want to connect to them. So this is the whole thing is called ESS, extended service set. One extended service set. Now, so we have defined many things. BSA, basic service area. BSS is basic service set. So this is the station, this is the area.
What is the area?
Area is this area, and this is this set. You see, area is by space, and the set is by the number of stations. So there is the basic service area, basic service set, extended service area, extended service set. Extended service area, for example, for BUFI is whole campus. And then ad hoc and exists at the same time as the infrastructure. So, those are the names. And here is the same picture all over again. RTS, CPS, data, app. The main different new thing is SIF, short interframe spacing. So between these frames there is a short spacing. Between the two RTS after this ACK there is a longer spacing called DIFS, distributed interframe spacing or something like that. So this is much longer, but these things are much quicker because they are expected right away. As soon as you send RTS, within one short time you are supposed to get the clear. Within one short time you are supposed to send the data. Within one short time you are supposed to send the acknowledgement. So that is SIF is the shortest amount that you have to wait. Everything that comes from the access point, it doesn't say access point on this picture, but everything that comes from the access point is listened by everybody. Everything has an address for who it is meant for. So it will say it is for you, right? But everybody can listen it. Same thing. Everybody can listen to the act. Well, so the reason they listen to the act is because they want to make sure that the medium is clear. Now they can start their diffs, so they can get onto the line. All I'm telling is that every station cannot hear other station, but every station can hear the access point. All right. Now, frame format. Now the frame is also special, so I have to tell you what the frame is like. It does not have just source and destination, it has 4 addresses. Address 1, address 2, address 3, address 4. And then it has lots of other things. So why there are 4 addresses? The reason there are 4 addresses is because the source and destination may be off the wireless, or may not be. So the thing is, you need a source, then you need the wireless transmitter, you need the wireless receiver, and then you need the destination. You need 4 people. So this station is trying to send to that server, right? So this is the source, this is the destination. But on the wireless, actually in this example there are 2 different situations. In this situation, coming from here to there, okay, let us start from here. This station wants to talk to that server, so this is the source and the transmitter. This is the receiver and this is the destination. Right? When coming from here, there are 2 hops, 2 wireless hops. First wireless hop, this is the transmitter, this is the receiver, and the second wireless hop, this is the transmitter, this is the receiver, and then this is the destination, this is the source. Right? So source and destination is different from transmitter and receiver. Okay? Clear? Alright, so you need all these addresses. You need the duration right up front. So you tell everybody that this frame is, how long it is, and frame control tells what kind of frame it is. Sequence control tells what sequence number it is. 1, 2, 3, 4, 5, whatever, 2 bytes here. Address, payload, CRC.
Why do you have so many addresses?
Alright, there is another frame which is type, and this one has a protocol version, type, subtype, to access point, from access point, more fragment, and retry, power, and blah. So this is some kind of control packet, and this type, if it is, it could be, for example, RTS, CTS, ACK, and so on and so forth. So that will indicate, let's see, 1, 2, 3, 4, 5, 6, 7, 8 plus 4, 12 plus 4, 16. So this is the frame control, 16 bits of the frame control, and this will indicate whether this is a RTS, CTS, whether it is going to the access point, coming from the access point, and so on and so forth. Alright, now addresses. Address 1 is the MAC address of the host, address 2 is the MAC address of the transmitter, address 3 is the MAC address of the router interface to which this access point is attached, address 4 is only used in analog mode. So there are many applications of these 4 addresses, and this is one shown here where it does not really have a destination address. It says that address 4 is used only in ad hoc mode. But there are situations where you are talking to the same network, same 802 network, and therefore you have the destination address. Well, basically what this is saying is that this access point might be connected to a router before the server. So to a router, and so that is the destination for anything going out. So MAC address is router interface. So this is the destination address. But if you are talking inside the same subnet, then you don't need the router, and that will be the address of the server, for example, if you are going to the server. So the number 3 is actually the destination address, to be correct. Address 4 is used only in the ad hoc mode. So that would be the origin address or source address. In Ethernet, if you want to send something to Google, on the Ethernet you need an Ethernet address. Whose Ethernet address you put in the destination field? You have to find your default gateway and find their MAC address. So on the Ethernet, at layer 2, it will have the source address of yours and this destination address of the default gateway, right? Once it reaches the gateway, then it will look that, oh, you are into Google. It will use the IP address of the Google to find which way to send you, right? And then it will find, oh, to go to Google, you really need to go to that router. So what is the MAC address of that router? So then again, every hop, you need to find MAC addresses to cross that hop. End to end, it is going from you to the Google, but that is layer 3. Right? Everything has to go through layer 2, every hop. Every hop you need the addresses. So this is this is explaining the same router thing. So the router is R1, it is going from here host to the access point to the router. So that becomes the third address. And the first address is the access point, which is the receiver. Second address is the source. And third is the destination. This is in 11. In 3, you just go from source to destination. Alright, the next detail is that the rate could be different. On Wi-Fi, even though we say 56 megabit, 200 megabit and 11 megabit, you really never get that rate. Those are marketing numbers. Those are the maximum possible bit rate. So you might be able to send a 56 bit per megabit per second, but lots of bits are lost because they collide in RTS, CTS, and retransmissions. So all of that you subtract. Plus, you may not even get 56 megabit if you want to go very far because the media is bad, the station has decided to run at half that rate. So basically 56 is the maximum possible rate, and your rate may be different. Your mileage may vary, as they say. The gas mileage that you see on the car, when you buy it, is the highest that you will get, the best you will get, but actual driving will be different. Similarly here, what happens is depending upon the noise. So here is a graph. Signal to noise ratio. Signal to noise ratio 10. 10 means bad. 20 means good. 30 means good, better, and 40 means even better. Now all of these in large scale, dB, decibel. Unfortunately, I don't even have time to explain to you decibel or the large scale, but basically 20 is 4 times better than 10, 40 is 16 times better than 10. Anyway, so this is large scale, and this is the bit error ratio, bit error rate. 10 raised to minus 7, 10 raised to minus 6, 10 raised to minus 5, 1, and 10 raised to minus 1 is 1. Every 10th bit would be bad. So that's really bad, right? You really don't want to run. You want to run somewhere around 3 to 6. 3 or lower, right? And so what you do is, if your signal to noise ratio is very good, means signal is high, noise is low, right here. If you are on this part, you can use a coding that gives you 10 raised to minus 8 bit error rate, and that is QAM 256. Now QAM 256, only thing to understand is that 256 is 2 raised to 8, and so you get 8 bits per hertz. Bit error rate means how many bits would be in error. Okay, that's totally independent. That's totally independent. They may correct it, they may not decide to correct it, but that is the error rate. If you didn't do anything, this is how many bits will be in error. If you're running at something at 10 raised to minus 1 or 10 raised to minus 2, you really need correction, because if every 10th bit is wrong, what are you going to do with those bits? Nothing. If the signal is low, then you get more errors, but you use the coding which is safer. You use QAM 4. QAM 4 means how many bits per hertz? QAM 256 was 8 bit per hertz. How much is QAM 4? 2 bits per hertz. That means you really have big bits and less error possibility, right? Yeah, right. So basically this coding has less error. QAM 4 has less error. QAM 256 has lots of error. Because if I start speaking at 8 bits per hertz, very few people will understand. If I say, yeah, yes, very slow, then a lot more people, less error. That's what it means. Is lot of bits per hertz, lot more errors. Remember, we talked about bits, hertz, and what? Yeah, that's what exactly here it is. That's why we need it. And the reason I teach that is because in wireless you can't do without those things. But the book doesn't talk about it. Okay. So when you are setting the signal strength, you are setting the power. So that's another variable. If you increase the power, you can go longer distance. But your other devices will hear it. So for example, this phone, when I put it near my microphone, you can start hearing it. Stronger means longer distance, but also means more interference with other people.
Right, but signals really strong because your rates can be faster too.
Yeah, right. So that's a good point. Is that if you have a high signal to noise ratio, you are doing 256. You are really getting your 56 megabit that you paid for. Otherwise, you will not get 56 megabit. All right. So anyway, so the idea is that rate is adapted. Adapted means changed dynamically depending upon the noise. So they see how good the bits are coming in. If the bits are coming in with a lot more error, see they don't pass the CRC, then they reduce the encoding. All right, is that clear? Power management. Power management is that the station can be dozing, both transmitter and receivers off, could be just receiver on or transmitter on, and the access points know that you are going to sleep. So when something comes and they say, well, they actually have an announcement right every few seconds where they announce that I have messages for station 3, 5 and 23. And if 23 is sleeping, they won't know that there is a message for them. As actually there are some people in the class. And then what happens is then we will say, okay, all right, we'll keep it and give it to you later, which I don't do right now. I am not buffering any messages. But effectively it is being buffered by the recording, right? But so they will announce the next cycle, well, I have messages for 353 and 23, right? Now 23 is broken up and says, okay, give me the message. And 23 can tell the access point, look, I'm going to go to sleep. And that's okay. That's always the protocol. That the wireless devices are all allowed to sleep, and they can negotiate that with the access point as to how long they are going to sleep, how often they will listen. They can say, well, I'm going to sleep and I'm going to listen every so many milliseconds. And many other standards have actually many different levels of sleeping. And so the access point will help you out by saving your messages as much as they can. So that brings us to the end of this chapter. So here are the 6 key points. First, CDMA. CDMA, now we use the new word, chips. So we use multiple chips to encode each bit, and it is used in Wi-Fi, just notice that. And so Wi-Fi comes in many varieties, 11, 11B, G, A, and N. Now none of you have seen 11, by the way. Because, we start with B nowadays, but there was an 11 before that. Plain 11. And then if you just CSMA, CA with 4-way handshake, RTS, CTS, data and act. So you know that, right? So that avoids the collision. Fourth is it has an extended service set. So there are multiple base stations. Each base station has its own basic service set and basic service area. And then there's an ad hoc. Then it has 4 addresses, includes the final destination, which may not be wireless. Final destination may be wired, right? And 11 has automatic rate adaptation based upon the error rate, and power management allows the stations to sleep. Those are the 6 key points.